This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Anything like remotely technology, like even the light in the car roof, I broke just by turning it. Like, I'm hopeless, really bad. Okay. All right, let's get cracking, shall we? Now the little red light's on, we can start. We all remembered to be here instead of over there, so that's a good start to the day. I don't normally at the start of a lecture I give out any notices. There's not really any notices today, except I decided to have two consultations since so many people can't come to one or the other. This is after the lecture on both lectures. If you can't come to either of these, you're welcome to drop by my office anytime, and if I'm there and I'm free, I'm happy to chat with you. Otherwise, if you want to make sure I'm around and can see you, just send me an email and we can sort out another time, that's fine. But otherwise, at those times, I'll be in my office or at least not very far away to chat to you. Does anybody have any other kind of housekeeping questions before we get cracking? No? All right, so we're right into it today. So on Monday, we were talking about matrices and vectors, mostly matrices, and we're going to talk some more about them today. We should finish this little bit of the notes on matrices and vectors today. So on Monday we were mostly talking, we spent quite a bit of time talking about determinants. Today we're going to talk some about inverses, and then we're going to start talking about row operations. Okay, so inverses. Suppose that we've got a matrix and it's square. N by n means it's going to be square. We say that it's invertible if you can find another matrix that's also square and it's the same size, so that you can do that little thing there. I don't like this lecture theatre. I feel like I'm underneath the board. If you can have A times by B, and you can also do B times by A, and those two things are equal, and whenever you do either of them, it equals to the identity matrix I. Okay? We call that B matrix that does that funny trick with A, we call that the inverse of A, and we call it A minus 1. Okay? So if you're thinking about matrices and the difference between matrices and numbers, if you had inverses of the real numbers, you'd think about it like, say, 2 times by 2 to the minus 1. Okay? And that's the same as 2 to the minus 1 times by 2, and that gives us 1. So on the real numbers, 1 is called the identity. Okay? And this is what we can do. When we're talking about real numbers, we could also say something like this. Okay, and we could keep on going. Whoops, 1 over 2 equals, times 2 is equal to 1. We can also do that. When we're doing matrices, we'll use this kind of notation. When we're doing matrices, you can't use this kind of notation. Okay, you only want to use like a superscript minus 1. Okay. This inverse is going to exist, here's the trick, if and only if the determinant is non-zero. Okay, so when you compare it with real numbers, that's like saying, what is this thing here to 0? If this was a 0, what does this mean? Well, it kind of doesn't really mean anything, okay, and you can't do it. So when you're talking about matrices, if the determinant is 0, then you can't find the inverse. Okay, A minus 1 exists if and only if the determinant of A is non-zero. If the determinant is non-zero, it's called non-singular. If the determinant is 0, it's called singular. That's an important thing to know. If you're doing something with software and you're solving some system of differential equations or something, if there's a problem with your system and the parameters and the way you've set it up, sometimes it will return an error, and the error will just say singular matrix. Okay, and it can't solve the problem, it says singular matrix. Singular matrix means the coefficient matrix of your problem has a determinant that's equal to 0 or maybe near 0. Okay, so that's an important term to know. If you go out and use pieces of software in engineering and it tells you singular matrix, this is why. If the determinant is 0, or if you're talking about big things, it's near 0. Okay. Prove that if the determinant is equal to 0, then the inverse does not exist. We're not going to do this proof, but the proof is in your notes. So if you're looking for something exciting to do on the weekend, you can try and do that. There you go. Okay, here's some notes. Not all matrices have an inverse. Okay, if you're not square, then you're not going to have an inverse. And if your determinant is equal to 0 and you're square, then you're not going to have an inverse. Okay, so not all of them have an inverse. If you do have an inverse, then it's unique. There's only one particular matrix that is an inverse for each other matrix that has an inverse. Does that make sense? It's a bit of a clumsy way to say it. Okay, but it's unique. You can't write down two different inverses for one matrix. It's always the same thing. Okay, there's another proof there which we're not going to do either. That's proof that the matrix inverse is unique. So what you do here is you say, let's say we've got a matrix A and it's got an inverse which is B. And let's say we've got a matrix A and the inverse is also called C, and then you have to prove that the B and the C are the same. So that shows that the inverse is unique. Okay, properties of inverses. Okay, let's say we've got two matrices and they've both got inverses. If you make a new matrix C times A, where C is just number, that CA matrix is going to have an inverse, and the inverse will be 1 over C times the inverse of A, so long as C is not 0. Excuse me. Okay, if you have A to the power of n, so you've got A times A times A n times, that's got an inverse of A to the minus 1 times A to the minus 1 times A to the minus 1 n times. Okay? If you take the inverse of an inverse, you get back to where you started. If you take the inverse of a transpose, it's the same as taking the transpose of the inverse. Those two things are commutative. That's the fancy word for that. All right, here's the tricky one. If you have A times by B, multiply them together, and then take the inverse of that, that's the same as doing the inverse of B multiplied by the inverse of A. Okay, the trick is you have to reverse the order. That's the only tricky one. And if you look, if you've got a string of matrices, A1, A2, A3, A4, and you multiply them together and take the inverse, when you multiply their separate inverses together, you have to reverse the whole order. Okay, and you can easily see that that's true. Let me write it down. Ew, that's not very nice, is it? Okay. If you have A times by B, take the inverse of that, right? And then if we multiply it by this one here, this is the inverse of that, so we should get the identity, right? Now the rule that's up there on the board says when you've got this inverse on the outside, you can put it on the inverse on the inside, sorry, as long as you reverse this order here. So that would be B minus 1, A minus 1. Right, and then these two join together to give you I. Okay, and the I doesn't really do anything because it's the identity, so you can take that out. And then those join together to just give you I. Okay, and you can see that if you didn't reverse this order when you put it over here, you wouldn't be able to do this little trick and everything wouldn't work out nicely. Okay, because remember, when you're doing matrix multiplication, the order of things matter. The order of things matters. So that's why the order has to reduce. Has to reverse. I'm a bit tongue-tied today. Okay, when you put the inverse on the outside. Okay, how do we find an inverse? Let's talk about how we do it for a 2 by 2. For a 2 by 2, here's a little 2 by 2 matrix. What you do is you find the determinant and you do 1 over the determinant, and then you get the entries of the matrix, and have a look what we've done. We've switched these two around and these two get a minus sign. Okay, and that's all you have to do for a 2 by 2. Alright, so we're going to do some examples of 2 by 2 inverses. If I can work this thing. Is that right? Is it clear? That's not too bad. Okay, find the inverse, if possible, of these 2 by 2 matrices. Whoops. Okay, so the first thing you have to do when you're finding an inverse is find the determinant. You have to do it for two reasons. One, you want to make sure it's not 0, And 2, if it's not 0, then you do this little thing here. Okay, so we're going to need it anyway. So find the determinant first. So this diagonal gives you 4, minus that diagonal gives you 2. Okay, so the determinant is equal to 2. You can say something like this. It's not equal to 0, therefore A minus 1 exists. Okay, that's good. If it exists, let's go and find it. And all you have to do is use this little formula here. Okay, so 1 over the determinant gives you 1 over 2. And then in the matrix, you have to swap these two entries. Well, that's not very exciting, is it? Swap those two entries. And with these two entries, you've got to stick a minus sign in front. That's it. Done. Okay. Now, in mathematics, almost always there's a way to check that you've got the right answer. So most of the time through this course, or lots of the time anyway, when we do an example, we'll talk about how to check that you've got the right answer, and sometimes we'll check and sometimes we won't. This time we will check. So the way to check for this one, if this is the inverse, then if I take this matrix here and multiply it by what we started with, I should get the identity, right? So let's just do that. A times by A minus 1. And you can multiply out those things and make sure you get the identity. All right, here's a trick to make your life a little bit easier. This 1/2 here is multiplying by this fraction. So if I want to, I could multiply this number here into the middle and I'd get 1 minus 1/2 minus 1 and 1. And then I'd have to multiply these two matrices together. Then I have to deal with fractions. If you love fractions, you can do that. If you don't love fractions so much, this 1/2, it doesn't matter when you multiply the 1/2, you can actually do it right at the end. So I can take the 1/2 out the front, right, and multiply these two matrices together. And then put the 1/2 back in afterwards, and then I won't have to deal with trying to multiply by fractions and add fractions together. Okay? You'll get the same answer, it's just a little bit easier this way. So multiplying two matrices, I get 4 minus 2 is 2. And minus 2 plus 2 is 0. 4 minus 4 minus 2 plus 4. Hooray! So we got the identity. So we found the inverse, and when we multiplied the inverse by what we started with, we got the identity. All right, does anyone have any questions for that one? Did you guys have a question, or are you guys okay? You guys right? Yep? Okay. All right, part B. Actually, let's just do this. Find the determinant, and we'll put straight lines here. Okay, first thing you do is find the determinant. First to check that it's not 0, and we're going to need it anyway. So this diagonal gives you 12, this diagonal gives you 12, and the determinant is 0. Okay, if the determinant is 0, then the inverse doesn't exist. Who said that? That's right. Yes, that's right. B, determinant of B is equal to 0, therefore B minus 1 does not exist. Okay, shout out when you get the determinant for this one. Giving out lollies now. Yeah, he said that. Very good. -2. Okay, this one gives us -20 minus -18. Okay, let's find the inverse. You want 1 over the determinant. So that's -1/2. I heard a funny story. Actually, I'm not going to tell that funny story. Okay. All right, finding the inverse, we switch these two numbers over. And with these two numbers, we change their sign. So we get a 3 and a -6. We're done. It's cool. Quickly turn it to silent before they start sending text messages. Okay. And once again, on the weekend, if you're looking for something fun to do, you can do this and you can show that what we started with times the inverse is going to equal the identity. But we're not going to do it now. Okay, does anyone want to ask any questions about that one? Yeah.
Should we just leave the fraction out in front?
Okay, that's a good question. All right, should we just leave the fraction out the front? If it divides evenly, I would divide it. If it's going to make fractions, I wouldn't. I'd leave it like that. And I'll tell you why. It's because most times when you find the inverse, you're finding the inverse to do something else with it. And to do something else with it, it's much easier if it looks like this than if it's got fractions in it. Because if it looks like this, you can do this same trick that we did here. Right? Pull the fraction out the front and deal with that at the end. If it's inside, then you've got to deal with it straight away. So if it works out nicely, I would. If it doesn't, I wouldn't.
What about larger matrix?
How do you find the inverse of a larger matrix?
Yeah, you don't use that.
That's a good question. That's a good question. Okay, this does not work for larger matrices, just like you said. And how do you do a larger matrix? We're not going to do that now. We're going to do that next week. I'll tell you how to do it next week. There's 2 different ways to do it. I'm only going to show you one. I don't mind which one you use. The one I'm going to show you, I'll tell you about it next week. Anyway, we'll do it next week. Okay. That's all we're going to do on matrix inverses for now. We'll talk about them again for larger ones later on. Okay. Let's finish this up. Here's a couple of special matrices. The zero matrix is kind of obvious. It's whatever size you need it to be, but filled with zeros. The identity matrix is whatever size you need it to be. It's got ones on the major diagonal. That's the one that goes this way. Pardon me. Hiccups. But the diagonal going this way has got ones on it, and then there's zeros everywhere else. A diagonal matrix has got numbers on the diagonal, but they don't have to be ones, right? So a identity matrix is a special case of a diagonal matrix.
So these have to be square matrices?
Zero, no. The zero matrix, no. But that's a good question, actually. No one's ever asked that before. The identity matrix, yes, has to be square, and it has to have ones on the diagonal, otherwise it doesn't make a proper diagonal if it's not square. And the diagonal matrix also has to be square. Okay? Okay. And an upper or a lower triangular matrix has got numbers in the upper diagonal part or in the lower diagonal part, and you always use that main diagonal that goes this way. And if you think about it, these last 3 special matrices, the numbers, not the zeros, the numbers are where the word says they are. So the diagonal matrix has got numbers on the diagonal. The upper triangular has got numbers in the upper, and the lower triangular has got numbers in the lower. Okay? So they're just a couple of special matrices. Remember when we did determinants, I said we'll talk about this later, The determinant of an upper triangular or a lower triangular matrix is just the product of the numbers on the diagonal. So if you want to find the determinant of a matrix like this, you just have to times all these numbers together. And that works for diagonal as well, times those numbers together, and it works for this one, lower triangular. Particularly for the diagonal one, we're going to use that property when we do eigenvalues and eigenvectors as well. Okay. That's it for that kind of stuff for a little while. We're going to do row operations now. Hands up if you've done row operations before at school. Okay. You know, I really like when I get to teach you something new, not something that you've done 5 times before. Okay. But there's a lot of people who probably haven't seen it. Row operations. Row operations on a matrix means you can multiply or divide a row by a constant. This is the kind of notation we use. We might write row 1 turns into 2 times row 1. Okay, so it's 2 times what it used to be. You're allowed to swap 2 rows, and this is how you would write that, or just with 1 arrow that goes backwards and forwards. You're allowed to replace a row by the same row plus a multiple of another row. So you might say row 1 goes to row 1 plus 2 times row 2. That's okay as well. All right. These are the things that I have seen people do and you're not allowed to do. I never want to see these again. Don't do them. All right? Some people will do row 1 times row 2. Don't do that. It doesn't work. It changes the whole question. All right? And people will do this as well. Row 1 divided by row 2. You can't do that. Here's one that makes your life really easy. Right? But it makes you get the wrong answer. You can't just times a row by 0. That's just like ignoring everything. And you also can't do one that goes like this. Don't do that, okay? Don't do any of these. I've seen all of them before. Don't do them. Only do the ones that are in the notes, okay? Yes, they make your life easy, but they also make your answer wrong. All right. Now we're going to talk about reduced row echelon form, and you do this by Gauss-Jordan elimination. Who did reduced row echelon form at school? Who did row echelon form at school? Does everyone who's got their hand up still know the difference? Yeah? That's very good. Okay. This is what reduced row echelon form is. A matrix A is said to be in reduced row echelon form if it satisfies these 4 things. Okay. When you look in a row and there's a number that's not 0 in that row, the first number in that row as you go across better be a 1. Okay, that's the first thing. And that 1 is called a pivot. Right? Now the second thing that is the second thing says, if you look where that pivot is, if you look above that pivot, if there is any above, or below that pivot, if there is any below, they better be all zeros. Okay? The third thing says that if you go down a row, the pivot in that row better be further to the right than the pivot in the row above. And the last thing says if any of the rows have only got zeros in them, you've got to shift them right to the bottom. Okay? That's reduced row echelon form. And I'll talk about the difference in a minute. If you get a matrix, it doesn't have to be square, it can be any size. If you get a matrix, you can put it into reduced row echelon form, and that answer is unique. Okay, that answer for reduced row echelon form, you all should get the same answer, or one of you is not in reduced row echelon form, or one of you made a mistake. Okay, you don't have to get there the same way, you can go lots of different ways, but you should finish at the same place. Okay, all right, which one of these is in reduced row echelon form? We're going to do this on here. Okay. Question says, is that right? Yes. Question says, which of these is in reduced row echelon form? This one. Does that satisfy those 4 things? Yeah, that's an easy one. Yes, it does. What about this one? Who says yes? Lost my microphone. Sorry. Waving my arms about too much. Who says this one is yes? Who says no? Who doesn't care? Okay, yes, it is in reduced row echelon form. If you think about those rules, the first number you come across has to be a 1. The first number you come across is a 1. Wherever those 1s are, there are zeros all below and above, if there is a below and above, right? The 1s always move to the right as you move down, so yes, that is. And any rows with all zeros are all at the bottom. So yes, that one is. What about this one? No, why not? Because of the 5. Here's a pivot here, and above the pivot there's a non-zero number. So that's not in reduced row echelon form. You can get this one there, but it's not there yet. What about this one? Why not? Great. This one's the one causing the problem there. You need a 0 above that pivot. What about this one? Yes, that's right. Okay, so reduced row echelon form, you've got those 4 things to look for. Okay, what's the difference with row echelon form? Row echelon form is not quite so fussy. All the 0 entry rows have to be at the bottom. Each pivot that is, as you move down, the pivot should move further to the right, but you don't have to have, you need to have below the pivots being 0, but you don't have to have above the pivots being 0. So this one is fine and this one is fine. All of them are in reduced, all of them are in row echelon form, but not reduced echelon form. Okay, so row echelon form is not quite as fussy. Okay, does anyone want to ask any questions about that? No? All right, how do we do it? You know, one reason this isn't my favourite lecture theatre, now everyone's quiet because they want to hear why. When you're in this theatre, if anyone is chatting at the back, right, what happens is the sound bounces, whoever designed this theatre did a bad job, it bounces right down the walls and it comes straight to me, right? So I can hear everyone chatting, even if it's really quiet. And it's really hard. And it also kind of bounces back and everyone can hear, okay? So I'd appreciate it if everyone was a little bit more quiet. Okay. All right, so how do we get a matrix in reduced row echelon form? What you do is you find the leftmost column with a non-zero entry, and normally that's the first column, right? You hardly ever see a matrix that's got all zeros in that first column. That's the column that you're going to pivot with first. You swap rows if you want to, so that there's a non-zero entry. You start at the top, and after you've done it a couple of times, you move down lines. So to start with, you're wanting a non-zero entry in the top corner. Okay? You multiply the pivot row by a number so that the pivot equals 1. Now there's a step that I sometimes ignore, and I'll talk more about that when we practice it. You add a suitable multiple of the pivot row to all the other rows to make the entries above and below the pivot 0. This is called pivoting. So what you do is you use that 1, or whatever number you've got, to make the zeros above and below. All right, and I'll show you how to do that. And then you choose your next pivot, which will be in the next column along if possible, and the next row down. Okay, so you work your way, you always work your way from the top left to the bottom right when you're doing reduced row echelon form. If you start mixing around in the order, you'll start going around in circles and you'll never get to the end. Okay, now we're going to do a whole string of examples. Oh, look, we're going to have heaps of time. Okay. All right, find the reduced row echelon form for this matrix here. When you're doing your row operations, you don't have to put the edges of the matrix in. Often I just put the bunch of numbers there. Ah, 3, 4, minus 1. Put a line underneath it though, because that will kind of make a line between each step of working you do, and it will just make things tidier. Okay, the other thing you should do is you should write notes about which row operations you do. Now, those of you who have done it before, when you write your notes, do you write your notes here or do you write them here? Top? Top? Okay. I know when I first did it, when I was at school, I did it the other way to you guys that do it, and better if I match U because then it makes sense. Okay, here's the 1 in the top corner. This is what we're going to pivot with. So we're going to use this 1 to make a 0 here and a 0 here. Okay, so in this row here I'm going to take row 2 and I'm going to turn it into row 2. Now to make this a 0 I would have to take 2 away, right? 2 take 2 is 0. And I can take that 2 away by taking 2 of these away, right? So if I take away 2 of those row 1s, I'll have this one take away 2, and that's going to give me a 0. And I want zeros below and above. There's no above. I want zeros below here. Okay, so that's going to give me a 0. I'm not going to change the row that I'm pivoting with. This is the one I'm pivoting with, so I'm going to write that down. No changes happen there. All right. Row 2. This row, take away 2 of those rows. So 2 take away 2 is 0. And then I have to do the same thing across the rest of the row. So here, 1 take away 2 of those would be the same as 1 plus 4. That's right, 5. Good. 5. This one will be minus 4, take away 2 of those will be minus 4, take away 6. Minus 10. Okay, so you do what you want so that the first number turns out right, and then you follow the pattern across for the rest of the row. Okay? Okay, this one here, I've got a minus 3 here. To turn this thing into a 0, I would want to add 3, so minus 3 plus 3 makes 0. And if I'm using this one here, I'd want to add 3 of those. Okay, so minus 3 plus 3 plus 3 of those row 1s is going to give me a 0 there. So minus 3 plus 3. 4 plus 3 of those gives me 4 minus 6. Minus 1 plus 3 of those gives me minus 1 plus 9. That's 8. And that's one lot of working. Okay? All right. Is anyone lost? No? Okay, I'm going very slowly because some people haven't seen this before. Okay, so now we've got this first column done, right? We've got a pivot here and we've got all zeros below. So now we can work on the next one. You can leave this as a 5 or you can turn it into a 1. This time it's easy to turn it into a 1 if I divide this whole row by 5, right? So I'm going to do that. Row 2 goes to 1/5 of row 2. And while I'm at it, why don't I just make this row a bit simpler too? 1 minus 2, 0, 1, oh. Minus 2, 0, 1, minus 4. Okay. When you're doing row operations, keep your eyes out to make the rows simpler because it will make your numbers that you have to deal with easier. Okay, so we've got a pivot in this column. Now we're going to pivot in this column and you're going to go 1 row down. So that's the one I'm going to use. Okay, and I'm going to use that to make zeros above and below. So this one will be row 1 turns into row 1 plus 2 row 2s because that's what's going to give me a 0 there. So that gives me 3 plus 2 of those is minus 1. Okay, before I go any further, I just want to say how important it is to go from left to right because, and like from the top corner and down like that, because this is a 0, it meant that when I did this row operation, this one stayed as a 1. If this one was not a 0, then when I did this row operation, I would have stuffed this one up. Okay, so that's why it's so important to work from the left to the right and the top down. Okay, otherwise you stuff up the work that you already did. Okay, this is the row we're pivoting on, so we're not changing that one. This one we just have to take away row 2 and that will be it. So 0, 0, minus 4 plus 2 is minus 2. Okay, so now we've done our pivot in our first column and we've done our pivot in our second column. Now we've got to do the last one. I want to pivot here, and I can turn that into a 1 pretty easily. Now it's a 1, we're going to pivot with it. Row 1 plus row 3. Okay, and again you can see how important it is to go from left to right, because this 1 doesn't get stuffed up and this 0 doesn't get stuffed up because you've already got a 0 here. Done. Okay, so we finished up with something that looks like the identity. That's not always going to happen. I'll tell you what it does mean though. It means that the matrix we started with has got an inverse. We can talk more about that later. Okay, does anyone want to ask any questions on that one? Say that again.
Step by step.
Say that again, sorry?
No, that means when the next matrix we put next instead of bottom.
Here.
Yeah, so it's easy to.
So you want to write next here.
Yeah, the next one we put at the top.
Sideways.
Yeah, then we put an arrow.
Okay. You can do that if you like. I would never do that. Okay. I always do my working going downwards. Whenever I'm doing mathematics, I always go downwards. If you're doing equations, you should only have 1 equals on each line. And when you come to do systems of equations, doing what you said is kind of like having more than 1 equals on the same line. Okay? So you could put an arrow going from here to here, but I would never go acrossways because it doesn't work with equations, and when you start using this for equations, it's kind of like doing that, if that makes sense. Yeah. Okay. Does anyone have any other questions? Yeah.
Sorry, can you just close out what you've written for those it's quite small, I can't see it.
Oh, is it? Sorry, I can zoom in a little bit more too, I think. Slowly, slowly, slowly. Okay, you want me to read them all out? Tell me when to stop. R2. Here?
Yeah.
So that's row 1 goes to row 1 plus 2 row 2s.
And what's the one above it?
Row 3 goes to row 3 divided by minus 2. And these ones as well?
Yeah.
The little subscripts, yeah, okay. So that's row 3, because I'm doing it on row 3. Row 3 goes to row 3 minus row 2. Maybe I'll be a bit neater as well. This one's row 3 goes to minus a half row 3. This one's row 1 goes to row 1 plus row 3. And that one's row 2 goes to row 2 plus 2 row 3s. How do you choose? How do I choose? Okay, so, all right. Okay, I'm going to answer this question, and I'm going to draw your attention to me because a lot of people come and ask me this question at a later date. Okay, so the question is, how did I choose which operations to do, right? These 2 operations I chose to do because I could see that I could divide by 5 and I wouldn't get any fractions and everything would still be nice and I'd have smaller numbers to deal with. Okay, and the same here. I can divide by minus 2 and it's still no fractions and everything looks nice. Okay, and the same with this one here. okay, so that I could get a 1. So when you're doing your row operations, keep your eyes out for common factors in a row and just make it easier, make your life easy. These ones here, the other ones, let's have a look at the first one. So this one here, I've got my pivot here. I want this to turn into a 0. The only row operations I can do is multiply it by a constant, but not 0. That's not going to give me a 0. Okay. I can switch it with another row. That's not going to give me a 0 here. Okay. The only other choice for a row operation here, wait, what? Here. Okay, so this isn't going to give me a 0, this isn't going to give me a 0, so I have to do it with this one. Okay, so I have to use another row. You're going to use the pivot row, right? So I've got this number 2 here. I want to add a multiple of this to give me 0. So if I take away 2 of these, I'm going to get 0. And so that's how I choose to do that. Okay, the rest of the row I don't care what happens to it. I'd have to do the same thing, but we'll deal with it later. Okay, so this one as well, I want this to be a 0. I'm going to use my pivot row. To do that, I have to add 3. So I want to do 3 times the pivot row. I can't just add 3, because that's not one of those rules. I have to do 3 times a row. Does that make more sense? Does that make sense to everyone? Yeah, and practice. And the more you practice these, you can kind of see the easy way about it. So this is not by any means the only way to do it. You can do it heaps of different ways. This is probably the most straightforward way to do this question. Okay? But most people here that haven't done it before will probably do more steps than this because, you know, I can see the way that's going to be most straightforward. Plus I already did it, so I know. Okay? All right. Let's do some more.
So when you have finished doing the calculations, do you put the parentheses on it or you just leave it like that?
No. Okay, so do I put brackets on it or anything like this? No. This matrix that we started with is A. The matrix that we finished with is not A because it's not the same as A. So you can't say A equals this now because it doesn't. It's something different. When you do row operations though, you would never do row operations like this and say just do the row operations, right? You're doing the row operations to solve a problem, and that's what we're going to do next week. So I'm teaching you this row operations technique so that next week we can use it to solve problems. Does that make sense? So normally you wouldn't finish here. That's a good question. Normally you wouldn't finish here. You'd have something else to do to finish solving the problem. That's what you'd do. Okay. All right. We might do this one and then we'll have a break, shall we? Stretch our legs. Okay, find the reduced row echelon form for this matrix. It's another square. It doesn't have to be square. This one is. Okay. All right, find the reduced row echelon form here. I've been very nice to us and I've put a 1 in the top corner already. So we can already start cracking with this as a pivot. Okay. If I want to turn this minus 2, so what we want to do is get all zeros here, right? To turn this minus 2 into a 0, I can't multiply by a constant. I'm not allowed to use 0, by the way. I can't swap 2 rows. That's not going to help me. So I have to add a row, and the row I'm going to use to add to it is the pivot row, right? So row 2 goes to row 2. To make this 0, I'd want to do plus 2. Minus 2 plus 2 is 0. So I want to add 2 of those. Okay. Take away 3 row 1s. 3 minus 3 is going to be 0. Okay, so that's the row operations I'm going to do. 1 minus 3, 2, 2. All right, this 1 plus 2 of those is 0. This 1 plus 2 of those, that's 0. This 1 plus 2 of those, that's 0. Plus 2 of those is 9. That stuffed us up, isn't it? Okay, that's the second row. The third row, we want to minus 3 of the first one. So this one minus 3 of those. This one minus 3 of those will be like 6 and 9, 15. Is that right? That's not right. What? Oh, I'm using 6. Just testing. Okay, 8 minus 3 of those is going to be 2. This one minus 3 of those is minus 6. Yes, shout out if I make a mistake, don't let me just keep going. We'll all end up in a big mess. All right, this one take away 5 of those. This one take away 5 of those. This one take away 5 of those. What's that, minus 3? This one take away 5 of those, minus 9. Okay, we pivoted on the first row. So that the first column, sorry. So that first column now is a pivot at the top and the rest of it is all zeros. That's nice. Okay. We've done the first column, move on to the second column. What are we going to do with the second column? Pardon? Well, these are all zeros, right? So you can't pivot with those.
I mean, swap the second row.
Oh, swap this one down? Yeah, we will. Yes, that's a good idea. We will. Why will we do that? Why will we swap this one down? Yeah, and you kind of, I mean, you can't pivot in this column, right? We're going to pivot in this column, and you can't pivot in this column with this one here. Yeah. Yeah? That's right. So we're going to swap this one down. While we're at it, let's divide by 9. 1 minus 3 to 2. All right, I'm going to do this row divided by 9. I'm going to do this row divided by 2, and I'm going to do this row divided by minus 3. Now, I haven't said where they're going because I'm going to rearrange them all as well. This one's going to go up. The bottom one's going to go up as well. 1, 3. And what else? This one's going to go down. Okay. All right. So I pivoted here. We're not going to pivot there. I'm going to pivot here with this one. So row 1 goes to row 1. Take away 2 row 2s because I want to do minus 2, so I get 0. This one minus 2 of those gives me. Did I stuff something else up? Did I? Pardon? No, I didn't write that they swapped. And then I'm going to send this to row 4. This one's going to go to row 2, and this one's going to go to row 3. Does that make sense? Yeah? Okay. This one take away 2 of those. This one take away 2 of these will be like 2 plus 6 is 8. Zero, 0, 1 minus 3. And this one will be row 3 goes to row 3, take away row 2. Sorry, I said I would be neater, and I'm not being neater at all. 0, 0, 0. The last row you don't have to do anything to. Okay. All right, this one I'm going to, so we've done this row, we're not doing this column, sorry. We've done this column, we're not doing this column, we've done this column. Now we're going to do this one. First of all, I'm going to divide this one by 6. Okay, nearly there. All right, so now we're going to pivot with this one. Row 1, take 8, row 3. That's the one we're pivoting with. Done, finished. Okay. These are nasty things to do on the board. All right, does anyone have any questions for that one? Yeah.
What's the benefit of using reduced echelon form compared to standard version?
What's the benefit of using reduced or echelon form? Here's the thing. If I was doing it, I would do row echelon form. Yep. There are some times when reduced or echelon form does make your life easier. So I'm not teaching you this because I love doing row operations. Okay? I'm teaching it to you because next week we're going to solve systems of linear equations, which is probably why you did this at school, right? The week after we're going to use it to find eigenvectors. Okay? Now, when you use it when you're doing a question, right, I will never say to you probably in an exam, almost certainly not say to you in an exam, find the reduced row echelon form. Okay? But there are some questions where you need to do it, like when you're finding the inverse of a 3 by 3, you need to do it. You haven't got a choice. There are some times, like when you're doing eigenvectors, where sometimes it's easier. Sometimes it's not, sometimes it is. And when we come to do eigenvalues and eigenvectors, we'll kind of do a bit of both, because it will be whatever's the easiest, that's what we'll do. Okay, so I've got to teach it to you so you know it, and we're going to use it sometimes, and sometimes we'll just do the not so fussy way. But you're right, it's more row operations, which is very tedious and boring and crap, okay? Okay, does anyone else have any other questions? All right, let's have a break from these row operations, shall we? All right, we'll have 10 minutes break. It's already 3 past, so we'll come back before 1:15, okay? And we'll do some other stuff. There's something else for you to do while you're waiting. he's got a MATLAB track while you guys are building. So that's not like the lecture where it's recorded, like it's just going to cut to All right. Let's get started, shall we? Did everyone read this question? So on Mondays I'm going to give you something, I'm going to tell you something interesting about a little piece of research. Sometimes it will be mine, sometimes it will be a friend of mine, sometimes it will be something else interesting that I found. On Wednesdays, I'll give you a little bit of a puzzle. Who thinks the answer is A? Who thinks the answer is B? Who thinks the answer is C? Hands up if you actually worked it out. You guys, you can both have lollies. And what was the answer? Beautiful. It's 3 metres. Can you... Oh, sorry, that was a bit wonky. It's 3 metres. If you get a rope around the earth and make it 20 metres longer, it's going to be 3 metres above the earth. If you get a basketball and stick a rope around it, or a little piece of string, make that 20 metres longer, it's also going to be 3 metres out. Isn't that amazing? It doesn't matter what size the sphere is. This is how you work it out. The difference between the circumferences, it's just 2 pi r and 2 pi r, what you started with and what you finished with. The difference is going to be 20 divided by 2 pi, and you get about 3 metres. Isn't that amazing? Okay, there you go. All right. Before we start, I've been told that next Wednesday some of the civil students have a geology excursion in the morning. Can I just have an idea of how many people will be gone? Okay, so you'll be back about 1:45, so you'll probably rock up about now. Can I also have another hands up? How many people, I can't remember off the top of my head, but there's at least one prac in the morning. I don't think there's a tute though. How many people have a prac in the morning that they won't be here for? The MATLAB prac. Is your hand up or down? You can't remember. No one can remember their timetable. If you know you've got a MATLAB prac on Wednesday morning, 1, 2, oh, there's lots. 3, 4, 5. Okay. All right. I'll have a look. Most of the MATLAB pracs are full, but I'll have a look when I get back to my office, and I'll put a note on the forum or something about what we might do about that. I'll have a think about it. Okay. What are we up to? Okay, so we're doing row operations, which I know are boring and tedious. They are, let's be honest. All right, who's chitter-chatting now? You 3 there. All right, we're doing row operations. We're not doing them because I think they're fun. We're doing them because next week we're going to use them for systems of equations, which is probably what you did at school. And the week after, we're going to use them for eigenvectors, which is probably what you've not done before. Okay, so everyone needs to know how to do their row operations. All right, we've done 2 examples already. We're going to do this one. The difference with this one, it's got an A, yeah. We've got a letter in here. Let's be a little bit careful when we're doing things. Okay, reduced row echelon form. Okay, remember we're going to work left to right and we're going to work top to bottom. I've been very kind to us again and I've put a 1 in this top corner, so we're going to pivot on that one. Okay, we want zeros, well there's no above, we want zeros below. So we want to turn this one into a 0. Row 2 goes to row 2 minus 3 row 1s, because that's going to give us 3 minus 3 is 0. Okay. Zero, 2 minus 3. Oops. What am I doing now? I did, didn't I? minus 1, minus 6, thank you, is minus 7. Anyone would think it was a Friday. Okay, 5 and 9 is 14. Okay, that's better. Row 3, take away 2 row 1s. Okay, we want to do 2 minus 2 so that we get this 0 in this bottom corner down here. 0, 1 minus 2 of those gives us minus 3. And A minus 2 of those, yeah, A plus 6. Don't panic, just write down what it is. Okay? There's nothing wrong with A plus 6. Are there any values of A where this is going to cause us a problem? No, not so far. Cool. Okay, let's make our lives a little bit easier. This one's got a common factor of 7. So let's get rid of that. Row 2 goes to row 2 divided by minus 7. That one? Yeah. Thank you. Okay, so we've done this column here. Now we're going to pivot in this column. We're going to use that one. Row 1 goes to row 1. Take away 2 row 2s. That take 2 of those is 1. That take 2 of those. That take away 2 of those is a 1. Minus 3 plus 4. All right, this is where our pivot is, so let's not touch that one. Row 3, we want to plus 3 of those. Whoops. Plus 3 row 2s. Zero, this one plus 3 of those. This one plus 3 of those will be A plus 6 minus 6 is just A. Okay, we've done the first column and we've done the second column. What are we going to do with the third column? Divide by A. Yeah, we're going to divide by A. Is that going to cause us any problems? For any values of A? Other than 0. Yeah. Other than 0. If A is not equal to 0, we can do divided by A, right? So let's do that. 1, 0, 1, minus 2. So we're going to do row 3 goes to 1 over A row 3. Okay, now this is only okay providing A is not equal to 0. Okay, so you should make a note of that because we probably better go back at the end and say what happens if A was equal to 0. Okay, so if we do that, then we get 0, 0, 1. Okay, and now it looks much more like normal and we can pivot on here. Row 1 goes to row 1, take row 3. Bless you. Row 2 goes to row 2 plus 2 row 3s. 0 and 0, 0 and 1 and 0, minus 2 and 2. Finished. Okay, that's not the end though. That tells us what the answer is if A is not equal to 0, but now we better go back and say something about what happens if A is equal to 0. So if A is equal to 0, let's go back to here where the A was the last time, and then we get 1, 0, 1, 0, 0, 0. Okay. Write it in reduced row echelon form. What are we going to do with that one if A is equal to 0? Pardon? Say it louder. Pardon?
You can leave it because the bottom row are all zeros.
We can leave it because the bottom row is all zeros, so you can have lolly. That's in reduced row echelon form already. Oh, look at me. Okay, that's in reduced row echelon form already, right? Because there's no pivot on the bottom row and there's zeros on the bottom row, that's fine, okay? So this question you get two different answers. This one, if A is equal to 0, if A is not equal to 0. This one, if A is equal to 0. I'll tell you what else that tells us, which we haven't talked about yet. This part here, see how this looks like the identity? That tells me that in this case there's an inverse. So if A is not equal to 0, there's an inverse. This one tells me there's not an inverse. So if A is equal to 0, there's not an inverse. And we'll talk more about that later on. Okay, does anyone have any other questions about that one? Should have said, yeah? Yes, you have to show both answers. If you get a question like that, you have to show both answers because the question says, find the reduced row echelon form, and unless you give both, you're not giving the whole answer. Yep. Is there any other questions? Moral of the story, be careful if there's letters in there. Be careful if there are parameters, they're called. Okay. Okay, what time is it? 24. All right. Next one, this one's an easy peasy one. Find the reduced row echelon form for this one. Okay, so once again I've been very kind and I've put that little one in the top corner so we can just pivot with this one. Row 2 plus 2 row 1s. That 1 plus 2, oh no wait, getting all excited. Okay, minus 2 plus 2 of those gives us 0. Minus 3 plus 2 of those, so that's 1. 1 plus 2 of those gives us 3. Row 3 goes to row 3. Take away, we've got 3, we want to make it 0, so we want to take away 3, which is 3 of those. 3 row 1s. Okay, this one take away 3 of those. This one take away 3 of those will be minus 6. This one take away 3 of those. Okay. These two are the same, that's interesting. All right, so we've pivoted in this column. Now we're going to pivot in this column and we can do it with that one. It's right in the right place for us. Row 1 goes to row 1, take 2 row 2s. 1 minus 6 is minus 5. That's the one we're using. Row 3 goes to row 3. Minus 1, we want a plus 1 to get 0, so I'm just plussing one of those. Row 2. Is that it? Yes, it is, you're right. That's reduced row echelon form. It satisfies all those criteria. That was an easy one. Does anyone want to ask any questions about that one? I'm going to say it again. Just because I did these steps doesn't mean you have to do these steps. You can do any steps you like, but you should end up with exactly the same answer. Okay? All right. We're going to do one more of these. Okay, this is the first one we've done that's not square. There's something else different with this one. This is the first one we've done where we haven't got a 1 in that top corner. Ah, who said that? Okay, it doesn't matter that it's not square. You can do row operations on any size matrix. Doesn't matter. You do the same thing. What are we going to do because we haven't got a 1 in that top corner? Somebody said it already. Switch them. We're going to switch them around. We've got a 1 here that we're going to use, so let's switch them around. What was I going to say? Okay, sometimes you might get no 1s in the first column. And we'll probably do some examples about that next week, I think, but not today. All right, so let's do row 1 and row 2 are swapping over, okay? Okay, so now we can pivot on this one here. Row 1 goes to row 1 plus 2. That's not right. There you go. Row 2 goes to row 2 plus 2 row 1s. This one plus 2 of those. This one plus 2 of those. This one plus 2 of those. What's that? 5. This one plus 2 of those, 4 and 26, that's 30. Okay, we want to turn this into a 0, so we want to subtract 3, so that would be 3 of those, right? Minus 3 row 1s. 0, minus 3 of those, minus 3 of those, that's minus 9. Oh, minus 3 of those, minus 1, minus 39. Pardon? Oh, you guys are fast. Too fast for me. Okay, here's another trick. If you're not that fast, and I'm not that fast, don't try to do these things in your head. Just write little notes on the side. Everyone can add up this one really quickly, but when you're trying to do this minus 3 times that, it's much harder. Just write it on the side, it doesn't matter. That's what I'm going to do, because I'm not that fast as all of you guys. All right, I'm going to divide this one by 5 to make our lives easy. And I'm divided by 5. Oh, let's make this one better too. And what can we do with that? Just divide by minus 2, yeah? Gives us 3. Oh, got dodgy 3s today. 4 and 20. Okay, so we've done the first column, move on to the second column. Row 1, we want zeros above and below, so that needs to be a 0. Row 1 minus 2 row 2s. nearly there. Okay, so we've done the first column, we've done the second column, now we're going to do the third column and we're going to pivot with that one. Row 1, take away row 3. 1 take 0, 0 take 0, 1 take 1, 1 take away 2. Row 2 goes to row 2, take away row 3. 0 take 0, 1 take 0, 1 take 1, 6 take 2. Finished. Okay, so this one wasn't a square. Because it's not a square, it means you're always going to have some columns or something that's not got pivots in it. Okay, if it was a rectangle this way, you'd have some rows that probably had zeros in them. As it's this way, you've got a column at the end that's got no pivots. That's okay. That's just the way it is. All right, does anybody want to ask any questions? No? I was going to say something and now I've forgotten what it was. I've said a couple of times, and I'll say it again. Now I forgot what I'm going to say again. Oh, that's what I'm going to say. We're going to use this row operations stuff next week for linear equations, which you've probably done, and then after that for eigenvalues and eigenvectors. If this row operations doesn't make sense, come and see me, okay? If you're having trouble with this, come and see me and we'll sort it out straight away, because you don't want to move on to that harder eigenvalues, eigenvectors stuff, and then you can't do this stuff that's from the beginning, okay? So make sure that you can do this stuff. Okay, I'm not going to switch over because we've only got this much to do before we do something else. Here's some tips. Use fractions, don't use decimals. If you have to do something and you divide by 2 and you get a half, write 1 over 2, don't write 0.5, okay? It's much easier to add a half and a third than it is to muck around with other things, okay? So always use fractions, not decimals. The other tip is keep these notes on the right-hand side that we've been keeping, okay? That little row 1 goes to row 1 plus 2 row 2s and something. Make sure you write them down. If you end up with something that you know is not the right answer, it helps you to go back and find where you made your mistake. And also it helps us when we're marking. The other tip I have is when you're doing row operations and you know you've made a mistake, and you look at it and you can't find where it is, and you look at it and you can't find where it is, go right back to the start, switch a couple of rows around and do it differently, okay? Probably your brain is doing something like 2 times 3 is 5, and if you keep doing the same things, your brain will keep doing 2 times 3 is 5. If you switch 2 rows around, you'll be doing some different sums, and you won't make the same mistake, which is probably a really simple mistake, okay? So that's a tip. Go back to the start, change things, and then do it again. Okay, these ones. All right, what would you do? So these little A's here, where these little subscripts represent numbers, what would you do if you started with a question like this? What's the first thing you would do? Beautiful, we're going to switch 2 rows. If this was a 1, let's use that one. If this was a 1, let's use that one. If neither of them are 1s, pick the one that you think might look the easiest. All right, what would we do with this one if you got part way and found this? Yeah, we're going to switch these 2, right? And then we can pivot with this one when it gets up to there. What about this one? What would you do if you got that far? Pardon? Yep, this column. Oh, no, don't switch columns. Yeah, no, don't switch columns. There's a tip. I'm glad that you said that, because now we can say, don't switch the columns when you're doing row operations, only do the rows. Okay, work with rows, not columns. You can change the solution of the problem when you do the columns, so don't do the columns. Yeah? Yeah, first and second. First and second what? What would you do? Swap? No, because you want to keep that pivot there. That's a good one. Don't move that. What would you do? This column's got a pivot in it. This column's got no pivot and you can't make a pivot. What's the next thing to do then? You want to pivot on this column, right? So probably you're going to use that one. Or if this one's a nasty number and that's a 1, maybe switch them and then do that one. Yeah? All right, does anyone have any other questions? No? All right, the next stuff to do is linear equations, and I think we've all worked hard enough on row operations today, so we're going to have an early minute. Okay.